middle of the road. What are you doing? It's a conspiracy. Okay. We are now recording. Let me go over just a couple of announcements. They're not all that crucial. I did finish on Friday. I thought I had anyway, the spring schedule. So that meant I could get back to grading papers. But then over the weekend, I thought of a couple other things I needed to do to the schedule. I took care of those on Monday. Then I got emails and phone calls of a couple other things they wanted to change on the schedule. So I think I got one of those taken care of and working on the other one. So that's finally, now I don't know why this is coming up because we're already open. So I'm going to close that for now. And then, so I did get caught up with the grading in this class, but I haven't got everything on Blackboard yet. So as soon as I finish all these, then I'll be able to start putting on Blackboard. But now I'm devoting just about all my office hours to catching up on grading. Except yesterday, I had bunches of students come in for advising, so that was an issue. Sorry, I talked too long. We'll start from current slide. Does anyone else have a question that you want addressed before we get going today? Okay, yes.
Question number 5 on the test.
Okay, I can't hear you. Could you speak?
Number 5 on the test.
Okay, now I can't answer a question. I can try to clear it up. Okay.
Number 10.
Oh, wait. Say again?
Number 10 on page 435.
Number 10 on page 435. Whoops, too far. Okay. This is, as she said, page 435. Let me get my pen set up. 435. This is problem set 16.2. And which one did you say, 10? 10? Okay. All right, here's 10. What is the wavelength of an electromagnetic wave with frequency 50 megahertz? So we're looking for wavelength. What's the symbol for wavelength? The lambda, okay? Okay, this is what we're looking for. What is the wavelength of electromagnetic wave with frequency? What's the symbol for frequency? Little f, and this is 50 megahertz. Now, what do we mean by megahertz?
That's like 10 to the 6.
10 to the 6 times 10 to the 6 hertz. Now, what a hertz is a per second. A strange sounding symbol, unit, but that's what it is. Well, do we have enough information to solve the problem? What else do we need?
You need the speed of light.
Speed of light, because this is electromagnetic radiation, so therefore we use the speed of light. And what is that?
3.00 10 to the 8.
Times 10 to the 8th. What's that? Meters per second. Excellent. Okay, so now we should be able to get the wavelength in meters. How do we do that? How do you do it? There's several approaches.
You just say lambda equals c divided by frequency.
Okay. You're saying lambda is equal to c divided by f. Is that right? Okay. So let's see if that makes sense here. 3.00 times 10 to the 8th meters per second divided by 50.0 times 10 to the 6th per seconds. Okay? I wrote it that way so you can see the per seconds go out. Okay? Giving us meters, which is a good thing for wavelength. Length is in meters. All right, we have to do a little bit of fiddling around with our units here. Let me move this decimal 2 places to the left. Not units, but places, 2 places to the left, and that will be If you make this number smaller, you make this one bigger by 2. So that becomes to the 8th. Okay, then this will be 0.5 will go into 30.0, 6.00 times, right? Okay. Okay, and that would be meters. So 6 meters is what it looks like. And that would be down in it happens to be on the page right across from the one you asked about, page 434. There is an illustration of the electromagnetic spectrum. You see 3 meters, and 6 meters would be just past that, and that would be somewhere around something greater than 10 to the 8th. No, sorry, 10 to the 6th. Actually, it looks like 10 to the 8th. Frequency of about 10 to the 8th. Well, our frequency was 50 times 10 to the 6th, which would be 0.6 times 10 to the 8th. So, yeah, that looks like a reasonable answer. Is that what they have in the back?
Well, it's not in the back because it's even.
Oh, that's even. Okay. But does that answer your question? Okay.
I have a quick question for you about the newest test you gave us.
Okay.
The 4th test.
Okay. And I'm glad you brought that up because I wanted to check and make sure everybody had a copy. Okay. Hold on just a moment. I looked like crazy for this, and I finally found it right where it belonged. But I thought I'd put it elsewhere. This is the one, find the period, right?
Correct.
Okay.
On number 9.
Okay, wait just a second. Does anyone need one of these? How many? 1, 2, 3. Do you have one?
No, I was going to give it to him.
Okay, well, I need to make copies. Last time the office was locked, and I went over to my office, and the copier is out. Okay, so how many need it? 1, 2, 3, 4. 4? Okay, I'll make 5 copies.
Somebody's it was 324. That's it. So just get this 2 hours. Because I got class at 1:30. We'll be out here. Stop lying, man.
I cannot believe this has happened again. The ladies were just in there when I came in and was setting up and got the new cord and all like that, and now they've gone and locked the office. And I thought they always worked until at least 5, and I can't see. They usually leave it open for the EMT class that follows this one, well, that comes in while we're still here, and they've locked the office. So I don't know what EMTs are going to do. Can y'all hang around till after class, and I'll make a copy?
We can go get a copy from study hall.
What's that?
I said we can go get a copy from study hall.
From study hall?
Yeah, do you got it on your computer? Like, do you got it? Is it on the computer?
No, all I have is a paper copy of this one.
Okay. I mean, we could print them out.
Yeah. Where are you talking study hall?
It's at the Arthur Shores.
The what?
It's at Arthur Shores.
Arthur Shores? Okay, will it be open after class?
Yeah.
Okay.
I think he was saying they could print one off your computer if you had it on your computer.
I don't have it on my computer. That's what I'm saying. Huh?
Yeah, that's what I was saying.
Yeah. But can I make a copy over there at Study Hall? Okay. Well, let's go right then. Okay. Which one did you have?
I'm sorry.
Yeah, that's all right. Go ahead. But
I have a question, number 9 on the test.
right.
It doesn't have the sound velocity in air. So what are we to assume to set that problem up.
Yeah, let's use the same as number 8. I'm sorry, I should have said that.
So
1090.
So okay.
Yeah.
And then one last question. On number 7.
Right.
Are we to assume that that's dry air? It doesn't specify.
How long will it take sound wave to propagate or travel through 150 meters? Yeah. The formula they gave you in the book, let's see.
I did it as if it were dry air. I just wanted to make sure.
Yes, that's a safe assumption.
Because some of the homework problems, it wasn't in dry air. It was like through water.
Okay.
And so I just...
Why am I not able? Oh, I haven't turned far enough over, that's why. Yeah. Use, the formulas on page 436. That's all it's asking, based on what they've given us here and the temperature they've told you. Yeah.
All right.
So, yeah.
Okay, thank you.
All right. Any others? All right. So right after class, we'll go to study hall and get the copies made, because I checked with my boss yesterday Friday.
When is it due?
As soon as you can get it to me. But we'll be finished the chapter fairly soon, and they'll have another test. So the
Can I
sooner.
take a picture?
What's that?
Can I take a picture?
Sure.
The front and the back?
No, just the front. Yeah.
That is right here?
No, that. Yeah. Okay. Any other questions before we get on to today's? Good questions, by the way. Good deal. Thank you. All right. I want to leave that somewhere where I can see it so I can go with you when we go. All right.
I'm good now. Like, after this.
Okay. Well, I'll need to make it for the others. Okay. So, I'm afraid that in my office, the copier, they said I don't remember what it was, a toner or something was out, and they didn't have the right stuff, so I don't want to risk going over there again. I went over there with Tyler last time, and he waited in the car, and I couldn't get the copier to work. And Friday they told me, oh yeah, it's down. Okay, are there any other questions before we move on to today's? All right. We're, as I said, on page 456. I can't read the numbers. Yeah, 456. We're chapter 17, basic electricity. This is the example 1, bottom of page 456. Two charges. Let me get a clean page here. Anyone need this any longer? Okay. Two charges, each with a magnitude of positive 6.50 microcoulombs. So let's represent this as a charge and that as a charge. And both of these are 6.50 microcoulombs. Okay? Positive, both of these. Okay? Are separated a distance of 0.2 centimeters. I can't write. Okay? Let me get my pen. 0.200 centimeters. Okay. Find the force of repulsion between them. Because they're like charges, they're going to be pushed apart. So there will be a force pushing them apart. And that's what it's asking for. Find the force of repulsion between them. What do we use? Coulomb's law, just above on the same page, Coulomb's law, and the force, positive or negative, the force between two charges is K. That's sometimes called Coulomb's constant, sometimes called the electrostatic constant. Q1 times Q2 divided by R squared. Okay? Now, here is your R. Here is Q1, and here is Q2. Doesn't matter which is which, they're the same. Well, all we need is Coulomb's constant, and that's given, again, just above this problem on the same page, 9.00 times 10 to the 9th. So it's 9.00 times 10 to the 9th. The units for are Newton meter squared per Coulomb squared. Newton meter squared per Coulomb squared. Multiply that by Q1. 6.50. What do we mean by microcoulombs? Same as before, but opposite.
10 to the negative 6.
To the negative 6 times 10 to the negative 6. Micro is a millionth. 10 to the minus 6 coulombs. And Q2 is also 6.50 times 10 to the minus 6 coulombs. Divided by, what is 0.2 centimeters? Notice these units have meters in them. How many meters is 0.2 centimeters? That's it exactly. 0.002 meters. Okay? Think of it, if that were a penny, 2/10 of a penny would be 2/1000ths of a dollar. Move your decimal 2 places over, cent, centimeter, dollar. Okay. So, there we have our problem set up. You can almost do this in your head. Probably the 6.5s are going to be a little hard to multiply in your head. But if your calculator has the EE or EXP key, that's how you do your exponentials. So 9, you don't have to put the 00. EE or EXP 9. You don't need to do the times 10. The E or EXP covers that. Times 6.5. You don't need that other 0. EE or EXP negative 6. Times 6.5. EE or EXP, negative 6 again, then divided by 0.002. And what do you get as an answer? Anybody? Just a ballpark figure. 3. Something pretty close to unity, but not exactly 1, but with hardly any exponent. No more than plus or minus 1. I would think plus 1 maybe. Anyone got it? Oh no, more than that. 9. Sorry, yeah, I was going the wrong way with my... Anybody? 9 EXP or EE 9 times 6.5 EE or EXP negative 6 times 6.5 EE or EXP negative 6 divided by 0.002. Anyone got it? Got something?
Yeah, I got 190.125.
1 what? 190.125. Okay, let's see how. Whoops, that's not quite what they got in the book, did I? Oh. I forgot the square our denominator. That's why we're off. Sorry about that, folks. You could take that answer and divide it by 0.002 again, and that would give it to you.
Okay. Well, what I have is a big number.
Okay, what is it?
95062.
95062 Is that it?
0.5.
0.5, okay. All right.
I did what you told me. You told me to.
Yeah. Okay. Yeah. And this would be in what? Well, here's a meter squared. That's a meter squared. Here's a coulomb squared. There's a coulomb. There's a coulomb. So we're left with newtons. Okay. Let's write it in scientific notation since most of the other was. So we'll move 1, 2, 3, 4 places over. So that'll be 9.5, but we only have 3 significant digits everywhere. So 1, 2, 3 digits. Look to the right. That's a 6. That bumps that up to a 1 times 10 to the, and we moved it 4 places, 10 to the 4th newtons. Exactly what the book has. 9.51 times 10 to the 4th newtons. Perfect.
So you're actually, oh, okay, that's right, because it's force. And
Yeah. Exactly. All right, good deal. That actually finished 17.3. Any questions on 17.3? Any questions on this? Okay. Then the problems are here. The odd numbers are in the back. I highly recommend you do some, if not most, of the odd number problems. There's only 4 odd number problems there. Shoot for them. Okay. Now, believe it's probably going to be good to go on and clear the screen here so we can start talking about 17.4. How fast would you say electricity is? Really fast? Okay. What do you base that on? Turn on a switch, lights come on, right? Except when Tyler walks in. No, okay, just kidding. Okay. Where's my roll? There it is. Okay. All right. And believe it or not, Tyler, I came in tonight. They were in the office, like they always are. So I thought, sure, I'll be able to make copies tonight. Came in here, set up, even had to swap cords. They were still in the office. And then when someone asked for a test, I went to make copies. They had just left and locked the doors before 5. So yeah.
So you can make copies off of the same thing, a printer.
What's that?
Or do you gotta have a copy machine? Because they got a printer up there.
They don't have a copying machine.
So, no, so you probably have to go to the library.
Okay. Yeah. No, D building. Yeah. But, okay. There's a copy room over there, but I bet you it's closed already. But I'll try my office again. They may have gotten it fixed so far this week. I don't know. It drives me nuts because they were just in there. And then they left well before 5. So I don't know. They're not under my control, but usually they're there. And usually they leave the door unlocked for the EMS people, but they didn't tonight. All right. Now, we were talking about how fast electricity is. Because when you turn on a switch, the light comes on. You think it's pretty fast. Actually, the charges moving themselves are moving incredibly slowly. Like maybe 1/10 of a centimeter per second or minute. It's just incredibly slow. Okay? But the lights come on immediately. Okay? How do you rectify those two sort of contradictory things? It's not the movement of charge that really matters. It's the electric field. That's what we're talking about here. So let's give a definition first. In terms of static electricity, an electric field exists where an electric force of attraction or repulsion acts on a charge brought into the area. So what creates the force? Another charge. Let's say we have a charge up here. You want it to be positive or negative? Second? Positive. A positive charge here. Now you bring some other charge in. You want it to be positive or negative? Negative, okay? Bring that into the proximity of this, and now it senses that. Now how does it sense it? There's nothing connecting it. That's because it comes within the field of this first charge. And because this is positive, that's negative, it's going to be attracted to it. Every time, guaranteed, because it's opposite charge. It comes within the purview of the field. So that's what they're talking about here, that an electric field exists where an electric force, or attraction or repulsion, ours is attraction, acts on a charge brought into the area. Okay? They show a picture in the text there of a balloon. And the odds are they just took the balloon, if they had nice dry hair, that won't happen in the southeast too much, humid as we are here, rub a balloon up with your hair and then stick it on the wall and it sticks to the wall. Okay? It won't always work here because we sometimes have a lot of moisture in the air. This guy, I can't remember where he was from, Illinois in New Jersey, so maybe one of those will be a little drier than we are. Okay? Now, and we talked about static electricity before, so I won't go into all that detail again. But anywhere there exists force, electrostatic force, Coulomb's force, there is an electric field. And the formula for that is on page 458. And the electric field, E, and by the way, that is a vector quantity, though they don't specify this, is equal to the electric force, the Coulomb force, the one we just were dealing with, divided by charge, per unit charge. Okay? Now, they put a prime on there, and the reason for the prime, that's the test charge. So if you had a field set up here, if you had a positive charge, and you brought a little test charge in. Now, most of the time on the test charges, they always assume they're positive, not negative. So we're going to change the last example. Positive charge here, bring in a small test charge, that's the Q prime. That is the amount of charge on the test charge, measured in coulombs. So if they give it to you in microcoulombs, 10 to the minus 6. Okay. So, yes.
Why is it a vector quantity?
Because it has direction. Okay? Forces have direction. You're always either pulling toward or pushing away. The field have the same directions as the forces. Okay? You don't need to know that. I just told you they will be vectors. Okay? All right. Example 1, then, at the bottom of page 458. I'll delete this just because I wrote it too big in the middle of the page. Let's do it. A positive test charge of 30 microcoulombs. 30.0 microcoulombs. And I'm going to write it like this. This is your test charge. What symbol do we use for that? What does the book use? Q prime, exactly, little q prime. Okay? That test charge, 30 microcoulombs. We need to express that in coulombs. So what would that be in coulombs? Just like before. What does micro mean?
10 to the negative 6.
Times 10 to the minus 6 coulombs. That's how many coulombs. Okay? It's placed in an electric field. The force on it is 0.60 newtons. So here's the force, 0.600 newtons, 6/10 of a newton. Okay? What is the magnitude of the electric field at the location of the test charge? See, we don't need to know beans about how far it is or anything else. All we need is what the force is at the point where it's introduced. So what will be the field? Just had it up there. Force per unit charge. Okay? Now that would be 0.600 newtons divided by 30.0 times 10 to the minus 6 coulombs. Now I'm not keeping this in scientific notation because your calculators can handle it. What would that be? Anyone? I can do it kind of in my head. If you move this decimal, say 2 places to the left, that would make the number bigger, so the exponent smaller, 10 to the minus 2, And that would be 60 divided by 30 would be 2.00 times 10 to the fourth, right? Newton per coulomb. Is that what they got? Yeah. 2.00 times 10 to the fourth newtons per coulomb. Now, field doesn't have it. Question?
That's what I was about to ask you. What?
Yeah, it doesn't have its own unit. Newtons per coulomb is about the best you can do. There is another unit. I can't remember what it is, but again, it's a compound unit like that. So, I just can't remember what it is, but it's equivalent to newtons per coulomb.
So typically are the answers for field going to be something like that?
Yeah, oh yeah, newtons per coulomb will be typically what the units will be. I don't think this book is going to use the other one, but I've taught physics from other texts that will go back and forth between the two units. This is the most common, newtons per coulombs. Okay. And what it is how much force per unit charge. That's exactly what you're talking about here. Okay. Any questions on that? Your calculator will take care of all that too, and hopefully did. Now, are any of you using electric fields right now? He is. I am. Anything projected on a screen, there are electric fields that are firing charges at the screen. Your television, color TV especially, it's firing a multitude of colors at the screen all at the same time in such rapid succession you don't even notice it, and that's what gives you color pictures. Okay? The illustration on page 459 shows an example of that. Electron beam deflection, and this is an old-fashioned TV. Newer ones are slightly different. Okay? In fact, I don't even know how flat screens work. Okay, but I know how the old tubes did. Now, page 459, they have a physics connection lightning safety. And this is really a bizarre little picture here. Number one, it's bright sunlight outside, so I thought, why is the guy squatting on a golf course in the sand trap? Well, they're illustrating the proper position to take if one is not able to get inside during a thunderstorm. Wouldn't it be safer if he ran over there to the trees? No, that's the worst place to be, anywhere where the tree can draw the lightning better than he can. The reason he squats is to give as small a profile as possible. I would say even better would be to lie flat in the bottom part of that sand trap, because usually they're dipped down. That would be even safer in my mind, but I guess he didn't want to get dirty. Okay. But they say crouching is better.
Did you know, I mean, you may know this, but I had no idea. We live on a golf course, and a few months ago there was a really big lightning strike, and one of the homes burned to the ground.
Really?
It's right on the green, you know, we're not on the greenway. We just
Right.
have a golf course in our neighborhood. And I was told that that's really common if you live you know what I'm talking about, where the golf course is in your backyard.
Yeah.
For homes to be struck by lightning.
Really?
Yes, and so I wondered, what is that? I mean,
God's vengeance on golfers? I don't know.
really don't.
I have no clue of why. Here's one possible, and this is far-fetched, but possible. All golf courses have extensive irrigation systems, and I wonder if the piping and stuff like that for the irrigation helps draw the lightning in.
I wondered if it had something to do with the fact the golf course is flat, and then there's an object. Like, what happens if lightning's? Does it travel? Like, does it?
Okay. Actually, what lightning tries to do is hit the highest thing around.
Right. So
And that would be the tree. Now, did they have trees in the yard, or do you know? Or
well, their backyard is the golf course. So
Right.
what I was wondering is it?
there was nothing for lightning to hit there, so it found the
goes to
nearest.
highest
hide thing, and that may have been their house or the tree right next to their house.
But then I heard that was a common occurrence.
Wow. Yeah. Don't know why, but that's interesting. I grew up on a farm in Georgia, and just recently my brothers who are still operating the farm sold the last herd of the cattle that we have. But it didn't happen often, but occasionally we'd have a cow standing on top of a hill and would get struck by lightning and she'd be dead like that. And other times it would hit, now this is back when we used wooden posts and barbed wire. The wood would not conduct the electricity, but the barbed wire would. And so if a cow was standing near the fence, when lightning hit anywhere on the fence, it would travel down the fence until it sets the cow nearby and jump across and get her. Because she was grounded, the fence wasn't. Doesn't happen anymore because most of the time we use metal posts, drive them into the ground rather than digging post holes. A lot easier, and supposedly they last longer. That's still, well, it doesn't matter now, we've sold all the cows. But those are other things that do happen, and the pasture would be because wide open space, it would hit the closest thing that was standing up there, and if it was a cow or the fence, but it couldn't go to ground until it hit the cow. Okay, believe it or not, that's all there was to 17.4. So right there is a problem set. Yeah. Problem set 17.4 on page 460. Again, 8 problems, do the odds, so there's only 4 of those that are odd. The odd answers are in the back of the book. All right. Now we move to simple circuits. Okay, this is 17.5. All right, good deal. Thank you. Now, are you going to be somewhere I can get you the test when I make copies? I'm sorry?
I got the test already.
You got the test already? I'm sorry?
Shannon sent it to me. I got it.
Oh, he sent it to you on the phone. Okay, thanks. Okay. All right. So 17.5 is talking about simple circuits. Now we have 2 kinds of circuits. Anyone know what they are? Actually, 2 types of current, I guess would be the better way to say it. I'll tell you one thing, this computer uses one kind, the light bulbs are using another kind. The projector is using the same as the light bulbs, okay? Your cell phone's using the same as the computer. And you know, I know what I'm talking about. 2 types of current. Yes, DC and AC. What in the world does DC and AC stand for? Direct current and alternating current. Okay. Now, early on, okay, way early on, the earliest discovery or use or interaction with electricity was what we talked about before. Static electricity, people charging up something and shocking their neighbors and having a big time with that. Okay? Never building up much charge, but a little bit. Okay? That was basically direct current. Okay? A charge builds up here, something comes in contact with it, the current moves from the charged area to the uncharged area, or from positive to negative, or negative to positive. Okay. Charges are moving. Okay. Once they discovered they could sort of harness electricity, actually the first guy who backed into this, and it was a total accident. Did I tell you this one before about Alexandro? No, not Volta. Galvani. Luigi Galvani. No. Okay. He was, of all things, not a physicist, an anatomist. He studied anatomy. And he was studying a dead frog that he had chopped the leg off of. The frog had been dead for a long time. It had been stored in formaldehyde. He cut the leg off, and he was studying, probably with, magnifying glasses and stuff, trying to determine the neural system, the nerve system, the muscular system, and stuff like this in that frog leg. And he didn't want to touch the sorry thing, so he had a set of tweezers. Let's just say they were made out of iron. And he had a probe that he was sort of separating, like a little needle type thing, that he was trying to separate these fibers, you know, the blood vessels, the muscle fiber, the nerves and neurons and things like this. And that was probably made out of copper or brass or something else. So he was holding the frog leg with his tweezers and went to touch to move around the fibers. And when he did so, the frog leg twitched. What a surprise that had to have been. I almost wonder if he fell on the floor or messed up his pants or something like that, because who would have expected a cut-off frog leg, a frog that had been dead out how many weeks or months or whatever, soaked in formaldehyde, and then to see the leg twitch? Scary. And he thought he had somehow discovered the nature of life. And he tried and tried and tried to sort of define that. How in the world did this frog leg come back to life? But it just laid there like a dead frog leg, cut off and everything else. After a while, I mean, he wrote it up as a little interesting side note, but he couldn't produce life, so he went on to other things. Well, one of his countrymen, Alessandro Volta, from Como, Italy, decided he wanted to follow up on this. And he found out it wasn't anything about providing life, it was the fact that he had two different metals and a good conducting fluid in between. And that created an electric current. And that electric current made the frog leg twitch. Because guess what? Electric currents make my arms move, my eyes move, my mouth move, you know. They do it all. We're electrical machines, okay? We have neurons that have different charges in them, and they are sending signals always throughout our body. That's why you hear, that's why you see, that's why you digest food, that's why you do everything you do, is because we are electrical machines. Now, most of that was direct current. So the earliest things were, and what Volta did, and guess what? We got the term volt out of it, so voltage. So what he did, he studied it in great depth and found out it was the two dissimilar metals, and that's what created a current if you had thing in between. Well, what he had just developed was a battery. Now, he called them POWs, voltaic POWs, P-I-L-E-S. Why, I don't know. I guess he stacked the layers like this and made stronger and stronger batteries. Okay? That is all direct current. Okay? Now, direct current is pretty safe. You usually don't build up too much voltage, but you can't operate it with it for a long distance, generally. Okay? About the length. And the reason this is direct current, coming out of the wall, that's always alternating current. Anything manufactured by a generator is alternating current. Okay? This is a converter that converts AC to DC. And that's why the computer, your automobile, your cell phones, flashlights, those are all direct current. Batteries produce direct current. Generators produce alternating currents. Okay? And alternating current, the charge really doesn't go very far. It does this. Okay, just that's all it does. Ever do is just goes back and forth and back and forth and back and forth. It's the energy of that, it's the electric field, that's what creates light and whatever else you're doing. Even in the direct current, where the currents are moving in one direction, the charges move incredibly slowly. It's the field that's set up when you turn on the switch or other thing. Guess what? Those charges are in every wire and every part of that device, so as soon as the field is established, then all the charges start moving. Not just the one where you turn on the switch, they all move at the same time because the field is set up at that instant. and that's why it looks like it's almost instantaneous. Okay? So this is what direct and alternating currents are. Now, what do we mean by a circuit? And hopefully what does the word circuit seems to mean to you? Anything? Say, if you went on a speaking circuit, what would that mean? You're going around somewhere, but ultimately coming back home, right? That's what a circuit is, okay? A circuit is something like this. This is be in a flashlight battery. Now, this doesn't look like a flashlight, but here you would have a switch, and somewhere over here you would have a battery, and they call it a dry cell, okay? And somewhere over here you would have a bulb. And I'm going to draw the bulb like this. Okay. So this is the battery, this is the switch, and this is the bulb. You close the switch, the battery sends the charge around, the light bulb comes on. Actually, the battery establishes the electric field and charges start moving. Not just at the battery, throughout the whole circuit. The only way it can work is if the switch is closed. Once you open the switch, no more movement of charges. The field is broken. There is no longer any field. So that's what's happening. That's a simple electric circuit. Okay? Now, what you need in an electric circuit is this. The battery is what we call sometimes the source. And what it's the source of? It's the source of energy. And I'll better define these words later. Okay? The bulb is often called the load. Okay, the switch just controls whether it's open or closed. But the other thing I haven't mentioned too much is the wire. That is the pathway, which would be the wire. You have to have a complete path for charges to move. If the switch is open, no pathway. Switch is closed, there is a pathway. So I'm going to close the switch. Now the charges move. So that's the three things. You need an energy source, you need a pathway, you need a load. Switch is not absolutely necessary, but that helps you control it. Okay? That's what basically makes a circuit. You have to have a completed loop in order for it to happen. So the electrons move from the energy source, the battery, to the load and through the wires. Okay. Now, let's go back to the battery. This is where the charges are given their energy. You're not using the charges. You're using the energy from the charges. Okay? The charges are fixed. They don't change. You don't create them. You don't destroy them. You just give them energy. That's what the battery's doing, giving energy to the charges. Then the charges move along the pathway, going through the load. The load uses that energy and produces light or heat or sound or whatever it is that the load is. If it's the iron that you're ironing your clothes, that's heat. If it's the radio, that's sound. If it's your shaver, that's produces the motion of your shaver. Whatever it happens to be, that is the load. The battery gives energy to the charges, and the load uses the energy from the charges. Okay? The energy, transmitted energy, is turned into useful work. Okay. So the source of the object that supplies the energy is the flow of electrons in a circuit. That is typically converting, a battery is converting stored chemical energy, basically coming from two dissimilar metals. Okay? That's exactly what's happening here. And just like Galvani's frog leg, okay? Two dissimilar metals create the movement of charge. Okay? So the source is the battery, the generator, the outlet, or whatever device is producing the electrical energy. The load, where the flowing electrons give up some of that energy that they got from the source to do useful work. That could be heaters, iron, motors, radios, computers, whatever. And another load would be energies use the rest of the electrical potential energy, and from there they must return to the source where they're energized again. All right. There is a decent picture of your battery there. Chemical energy is changed into electrical energy in that what they call the dry cell battery. Now what you're actually, the casing of that dry cell is one metal, that's zinc usually, and the inner core of that is a carbon rod. Carbon's not much of a metal, but it acts pretty much like one, and that dissimilar metal between carbon and zinc that creates, it's usually about 1.5 volts. Okay, and we'll talk about that in a minute. In between that, you have a wrapping of alternating sheets, and the paper that's in between is soaked with, even though it says it's a dry cell, it's soaked with a chemical that transmits, okay, the charge. So it allows the charge to go from the zinc to the carbon, because the carbon in the middle is positive charge, the zinc can on the outside is your negative. And that's why you put your batteries in with the tap toward the positive side and the flat end toward the negative side. Now, the energy we're talking about here, stored in the battery, is called electrical potential energy. I let that out when I was reading that. Electrical potential energy. So quite often we talk about the battery having so much potential difference between the plus side and the minus side. And by the way, on our diagrams here, the long bar is usually the plus side, the short bar is usually the minus side. Okay? So that would be the battery facing that direction with the knob on this side, the flat end on that side. Now, so we talk about the strength of the battery in its potential difference between the plus and the minus. What's the difference in that is maintained there? That difference in potential is what enables the battery to give charge to give energy to the charges, and we call that the voltage of the battery. The potential difference, and that is measured in volts, which is energy per coulomb. Okay, joules per coulomb. I should say it that way. A volt is a joule per coulomb. The symbol for volt is also, that's the unit for volts. The symbol is also V. That's the one that they use the same symbol for both, is equal to energy per charge. Charge being Q. So the units are volts or joules per coulomb, and the symbol voltage is energy per unit charge. Don't let the two V's confuse you. They're both capital V's, named after Alessandro Volta. Now, there is a little diagram. It's in your book, and it's something like this is in just about every physics book I've seen in recent times, and that's this. It's sort of an analogy between a water pump and a battery, okay? What a battery is doing here, here's the battery, this is the power supply, the energy source, electrical energy source. Here's the wiring, there's the load, the light bulb, and then they come back, whoops, okay. Here we have a problem, and I'll tell it to you in a bit, okay? The battery provides energy. It jacks up the energy of the charges. Now here's the problem, and people blame it on Benjamin Franklin. Benjamin Franklin? What did he have to do with electricity? Okay, he actually did a whole lot in the early days. Remember his experiment of flying the kite in the thunderstorm? Because he was convinced lightning was a form of electrical energy. He was wise, otherwise he'd have been dead, but he had a key attached to because it was out there in the rain and that conducted electricity well, but he hung a key that well before it got to him, and the lightning, when it did discharge, it went down and went to ground on the key rather than using his body. Smart man, okay? But Benjamin Franklin sort of arbitrarily said, well, let this side be positive and that negative. He had to name the two different charges something. He named them positive and negative. And whoever it was, either him or someone else, decided the electrons would be negative, and they didn't even know about protons or electrons probably at the time. They would be positive. Well, the sad news of that is it's the only thing in physics where the energy goes from high level to low level to high level. Because the electrons being negative, that's actually your low potential. And the positive charge is positive is your high potential, but the flow goes in the opposite direction. Because electrons go from the negative pole to the positive pole. But everything else in physics and in nature, we always say it goes from high potential to low potential. So what they do, and it's sort of awkward, the actual electron flow is in this direction, but the conventional charge, which would be the positive charges, if there were any positive charges, would be flowing in this way. So you have this big controversy. Well, it's not a controversy, it's just a sort of ironic situation that you have, because they're negative charges, they move in the wrong direction. So that's why they're showing the electrons are given energy in the battery, and then they flow in this direction, flow through the light, heating up the filament, making it glow, and then coming back to the battery on the low end. And that's why they say high energy electrons here, low energy electrons there, because the battery has given them more energy. Everywhere else in physics, you would have the flow going in this direction because it goes from high energy to low energy, plus to minus. It's just the electrons are negative, so they flow in the opposite direction. But forget that for now. How is that analogous to the pump? Well, the water is like the electrical charges here, like electrons, okay? The pump is like the battery. It gives more energy to the water, and this what pumps it up in the tower. That looks like the big peach down in Clanton, right? That's the water tower down there that you see off the interstate because they grow so many peaches there. Pumps the water up there, giving the water energy. Then you can draw water from that and turn a turbine and produce energy, okay? This would be like your light bulb. That would be the load. That's doing the work that the water, the energy of the water had been given by the pump, using that energy to turn the turbine to do whatever you want to with it, okay? Same thing here. The battery is like the pump. The wire is like the pipe. The charges are like the water. And the turbine is like the light bulb. That's the analogy between a water system and electrical system. And it's a pretty good way to think of it, okay? Now, any questions on that? Does that kind of make sense? Okay. So that was your voltage source, the battery. Could be a generator that you're connected to the wall with. Okay. Now your conductors are your wires. Okay. Let's see if they have a picture of them. No, they don't. Okay. I wish they did. So let me go back to the other slide. Okay. Go from here. Oh, current slide, sorry. Okay. This is not a very good picture. Ooh, I've got to get my color back. Okay. Let's just say this is your wire. Okay. There's your wire. Your charges flow down the wire. Now, this is not really very accurate here, but you get the idea. That's if it's a good conductor. Okay? If it's a poor conductor, the charges hit all sorts of obstacles as they're trying to go and get bounced all over the place, and it takes a long time. In fact, probably a lot of energy is spent just forcing the charges through the wire. Okay? Now, any of you cook on an electric stovetop? Okay? When you turn on the switch for that, that eye gets really hot, doesn't it? You know why? It's a lousy conductor. Okay? And the charges that are trying to move through there are meeting all kinds of resistance, and they heat up. And that's what cooks your food. That material is, I think, generally nichrome. Nichrome. And that's made out of nickel and chromium, which are not very good conductors. And therefore, it heats it up. In your oven, if you have an electric oven, that thing that goes around there, when you turn it on, it turns red. That's what heats it up. In your iron, somewhere in there is probably nichrome or something else. It's a lousy conductor. You put a big potential difference across it, you force electrons through, they run into all sorts of resistance, and they heat up. Okay? Your hair dryer probably has a coil of something like that in there, and the fan then blows the air over the coil, and that's how you use your hair. Anything that produces heat like that typically has a poor conductor in it. Now, the wires that go from the plug to your device, hey, you want a great conductor in there. So most of the time we use copper for that. It's not the best conductor, but it's just about the best conductor. Actually, the best conductor of natural materials, silver. Why don't we use silver wires rather than copper wires? Way too expensive. Plus, the other thing is copper is flexible. Silver is very brittle, so your wires would be very stiff, and you wouldn't want to use them. And besides, people would steal them all the time. Never mind. They wouldn't do that, would they? Okay. Now, if it's a really lousy conductor, we call it an insulator. Okay? This is a poor conductor. But if you have something that hardly will let any charge through at all, that would be called an insulator. Okay? Thank goodness for insulators. Do you see any insulators in the room? I can guarantee you on a couple. Okay? This thing right here, yes, that would be. Because probably there's wires and stuff in there you don't want when you touch that to get shocked. I would have been if that was a good conductor. So yes, the outside, the plastics, the rubbers, this light switch here, I guarantee you that's a great insulator. Because somewhere back there is actually current, and you don't want that transmitting the current to you when you flip on the switch. So yeah, we have lots of good insulators. In fact, here are some more. I don't want to mess this up. The coating here, this rubberized or plastic or whatever it is coating, that's an insulator. There's wires going through there. They're carrying current. We don't want that to hit us. So yeah, these are coated with insulators. The box here is an insulator. This is an insulator. That covering there is an insulator. In fact, when you strip the wire, you're taking off the insulator so you can get to the actual good conductor. So those are what your insulators are. So, there are a small number of materials that are called semiconductors. And they are rather strange materials, okay? A semiconductor fall between conductors and insulators in their ability to conduct electrical current. Their importance is due to the fact that these materials, under certain conditions, allow current to flow in one direction only. Silicon is a semiconductor used in transistors and integrated circuits, ICs they're called, and semiconductors are neither good conductors nor good insulators in their pure form. However, they become excellent conductors or insulators when an impurity is added, and selenium is one of those semiconductors used in the process of making photocopies and other things. So everything like that. Your telephone you're messing with right there, your computers, your calculators, they are filled with semiconductors. They allow the charges to go at certain times, at certain ways, you know, and they're all controlled by the parameters that allow the charge to go or not. Okay? And that's how we send signals and all sorts of things there. There's one more classification here, and that's a superconductor. Okay, remember I said copper was a great conductor, not the best. Silver is even better, but even silver has some resistance. Copper has some resistance. Over time, they will heat up a little bit, you know, and not conduct as well as they could. What a superconductor is something that conducts perfectly with absolutely no resistance whatsoever. So good, in fact, that once you get current moving in a superconductor, you can remove the battery or the power source, and it keeps going forever. Perpetual motion machine, which weren't supposed to happen. You know, it's really an unusual phenomenon. I bet you, I don't know this for a fact, but I bet you just about as many Nobel Prizes in physics have been won with people who worked with superconductors as just about any other single device, because those are so fascinating. Problems with them: they only operate at super cold temperatures. So you would think that would be something we'd want to use all the time, but you have to keep your superconductors incredibly cold. So there you use most of your energy. You would be saving from losing electrical resistance. You would be losing by heat. Okay? So I was talking with a student after class today about a high-speed train in Japan that runs on a superconductor that creates a very strong magnetic field. We'll talk about this a little bit later, and it actually elevates the train off the track, and then there's no friction between the train and track. So they can go at incredibly high rates of speed. Okay? That's a superconductor. Superconductor is a material that continuously conducts electrical current without any resistance. Okay? But it has to be cooled to very low temperatures. Okay? Usually near absolute zero, which is as cold as you can ever go. Heikki Kämmerling-Onnes discovered superconductivity back in 1911, shortly after he discovered how to liquefy helium gas. And that says really, 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 really cold. Okay? He determined that mercury metal lost its resistance to the flow of electricity at temperatures just below 4.2 Kelvin. That would be minus 200. Trying to think what the equivalent is. Way down there, 269 degrees or so Celsius, which would be minus 400 and some odd degrees Fahrenheit. I mean, 469 or something like that. Really cold, incredibly cold temperatures, as cold as you could ever get just about. Okay? And he discovered that then. He determined that mercury metal lost its resistance to flow electricities then. That's the boiling point of helium, by the way, and scientists are currently finding materials in which superconductivity exists at higher temperatures, but still they're at like minus 83 Celsius, which would be minus probably 100 and some odd Fahrenheit. I don't know what they've got up to now. Okay, so that's the conductor. That's the pathway through which the current flows. The load converts the electrical energy into other forms of energy or work. In a light bulb, now we don't have that many incandescent light bulbs anymore. You probably have seen them and used them in your life. You probably still have some in your home, but they actually heated up a filament so hot that it glowed. So most of the energy in the electric light bulb was spent on heating, not on producing light. And that's why the bulbs get very, very hot. If you touch one that's been on a long time, you're going to burn your fingers, right? So you usually change your bulbs after they cooled off. Okay. Other types, like fluorescence, they use a completely different technology. And nowadays, and I bet you what's in that projector there is called an LED, light emitting diode, which is a not brand new, but a much newer technology that works quite well. But that's not all. Heat, light, sound, whatever, that's the load. It actually takes the energy from the battery that came through the wire, the current through the wire, uses that energy to produce whatever the thing. Okay, let's go back to the wire for a moment. The book is organized rather strangely. What is moving here are charges. Charges are measured, the symbol for charges are Q, and they're measured in coulombs, named after Charles Coulomb, a French physicist who I think lived about the same time as Benjamin Franklin. He may have been a little bit later. If they lived at the same time, I almost guarantee you they had to have communicated some, because Benjamin Franklin at one time, I think, was our ambassador to France, and it was about the time that electricity was just getting going. So I bet you he did work with some of those guys. Coulomb was one. Ampere was one. There were several high-level French scientists who he may have collaborated with some of them. Okay? So what is current? Current, I can't spell, is the flow of charge. What do we mean by that? It's current. The symbol for current, where they get this, I don't know, is I. I is equal to Q over T, is the time rate of change of current, the flow of current, current going through a wire over a certain time interval. Okay? The unit for current is ampere, and ampere is a coulomb per second. These are can't think of the word, I want to say parameters. That's sort of right. But that's the symbols representing the thing, current, charge, and time. The units are ampere, coulombs, and seconds. Okay? So 1 ampere is 1 coulomb flowing in a given second. Now, just to give you an idea, a coulomb is a measurable amount of charge. Okay? We can even measure down to microcoulombs. Millionths of a coulomb. Okay? But actually the smallest unit of charge is the electron. That's what actually holds it. Okay? And get this. They don't measure current in electrons per unit per time. Otherwise, here is the thing. The 1 coulomb is 6.25 times 10 to the 18th power of electrons. Okay? An electron is so incredibly tiny, you would need 6, 250, comma 000, comma 000, comma 000, comma 000, 1, 2, 3, 4, 5. That many electrons to make 1 Coulomb of charge. I don't even know how to name that. This would be 1,000, that would be million, that would be billion, that would be trillion. So that would be 6 million trillion electrons. I mean, enormous number of electrons. So we don't use that. We use coulombs. Much bigger unit so we can use smaller numbers. Okay? So 1 ampere is 1 Coulomb per second. That many electrons passing in a second. Okay. Now, from now on in this book, even though that earlier illustration showed the flow of electrons, from now on when they're talking about things, they will assume a positive current, which is often called a conventional current. And it always goes from high potential low, from the plus to the minus, where you know that the electrons are flowing in the opposite directions. So in this book, we'll assume the charge carriers are positive. They're really not. The charge carriers are usually electrons, which are negative. But we'll assume that so we can have everything going right. All right, so let's go now to the concept of your voltage, which is your what gives the energy to the charges, right? Joules per Coulomb, energy per unit charge. So let me clear this out of the way so we can talk about voltage. So your potential difference, that's the difference in potential energy, okay? And that's measured in volts. And it has a name, voltage, too, by the way. And that is 1 joule. By the way, joule is capitalized because it's named after James Prescott Joule per Coulomb. And 1 Coulomb, named after Charles Coulomb. So that's capitalized. So 1 volt, named after Alexander Volta, so it's capitalized, is a joule per Coulomb. And back when we were talking about current, 1 amp, named after Andres Ampere, is 1 Coulomb, named after Charles Coulomb, per second in 1 second. Second's not named after anyone, that's lowercase. Okay. So a volt is a joule per Coulomb. Now, sometimes they'll call that, rather than V, they'll call it E. Now that's most of the time now we use E for energy. This is not energy, it's related to energy because joules are energy, but it's often, the old name for it was EMF, which is a misnomer itself. It was called electromotive force. It's not a force either, okay? So that's why they just say EMF, they don't say electromotive force, or they use capital E to stand for EMF, but capital E usually stands for energy, so it's all a mix-up on what unit, on what parameters they use, okay? But usually what we're interested in is not particularly what the voltage is, but it's what the change of voltage is, the voltage drop, delta V, final minus initial, okay? And the volt was named after Alexander Volta, as I said before. It's both the unit of electricity, of voltage, of potential difference, and also the voltage drop. So it's used for lots of different things. All right, now we get into what we were talking about before, and I've already erased resistance. Why your stovetop heats up and turns red. Why, your iron gets hot. That's because of resistance. If it's a poor conductor, it has a lot of resistance in it. So what is resistance? It's the opposition to current flow. It's called resistance. It's given the symbol capital R. That's what resistance stands for, resistance. It was studied quite extensively by a German physicist named Georg Ohm, O-H-M. That was his last name. Rather strange last name. Okay? His first name was Georg, G-E-O-R-G. Almost like George, but this is pronounced as a long A sound, Georg Ohm. Okay? I don't know if y'all remember The Sound of Music. One of the, I think, the head of the household in the whatever Von Trapp family, you know, I think his first name was Georg. The first several times I watched the movie, I thought, what is she calling him? You know, when the Countess was his date, you know, she kept calling him Georg. I said, what is that? What kind of name is that? Then I realized it's George in German. Okay, but anyway, he studied resistance. And what he studied, though, he looked at the current, and he looked at voltage, and he noticed that the voltage was directly proportional to the current. And the constant of proportionality was what he called resistance. The higher the resistance, the higher voltage to produce the same current. Or the more current you flow, that flows there, if you have more resistance, it requires more voltage. Okay? That is your relationship. And this is what he called resistance, the constant proportionality. So they named the unit for resistance after him, an ohm. So what do you think? Let's say we had 5 ohms. What symbol do you think they would have used? Voltage was V, current is coulomb, ampere, charge is coulomb. What unit would they use for resistance? An ohm. So what would be the symbol for ohm? Maybe a capital O? What would be wrong with that? That looks like a 50, doesn't it? So you can't use capital O. Yes, okay, you got it. So sometimes when we can't use an English letter, we'll go to the Greek alphabet. And the Greek letter for O is Omicron. But Omicron also looks like a 0. So you can't use Omicron. But in the Greek alphabet, there's another letter that starts with O. And that's not following mu and nu like M and N and O. That's Omicron. It's at the very end of the alphabet. And that's your omega. So the omega is like this. That's your capital omega. The little omega looks like that. It looks like a W. But the capital omega is like that. It's like a horseshoe, kind of. Okay? That's the unit they use for resistance, ohms, capital omega. Doesn't look like a 0, so you can use it. You won't get confused. So this would be 5 ohms of resistance. Yes, that's understandable without being confusing. Okay. Now, do you want a dumb story to go on top of this? The reciprocal relationship to resistance is something we call conductance. How easily something transmits current, charges, okay? So it's the reciprocal, and so it's called conductance, okay? It's equal to 1 over resistance. And they decided they wanted to have a unit for conductance. But they couldn't use capital C. They had already used that first for coulombs. They had also used it for degrees Celsius, but you have to have a degree symbol by that. So yeah, the letter C was out of there. They can't use the letter C. So what letter, in fact, what would we name that unit? Anyone have any clue? They decided to name the unit for conductance a mho. A mho? Why would they name it a mho? And especially spell it some crazy way like that. Why do you reckon they did that? Look at it carefully. It's what?
Because it's like has the same letters as home.
And it's exactly spelled backwards. Because it's reciprocal. It's backwards. It's the opposite. So they named it, boy, physicists are a little crazy, aren't they? They named it a mo. So what unit were they going to give it? Okay? They couldn't give it an M, mo, because that was used for meters. Can't use M, so what unit would they use for that? Well, no, they use that for angular frequency. So, no, that's already used. Here's what symbol they used. What is that? They flipped over because it's reciprocal. That's not any symbol in anybody's alphabet. They just took an omega and flipped it over because it was reciprocal. They are really nuts, these physicists. They're crazy, crazy people. But you're not responsible for that, so I'll take this off the board. That was just a dumb story. True, but dumb, or whatever. I can't get my eraser to come up. So let's get rid of all that. Okay. All right. So that's what resistance is. Basically is the opposition to current flow. Resistance is the opposition to current flow. Now, there are four things, major things, that determine how much resistance the material has. Like I've already said, silver is our very best naturally occurring resistor unless you get into the superconductors at really low temperatures. Now here's a strange thing. The best conductors at normal temperatures do not make good superconductors at low temperatures. They're really weird things that make good superconductors. It's really a strange situation. Okay? But there's four features of a material that helps determine its resistance. One I just mentioned, and this is the fourth one they say, is the material. The best one is silver, but just behind silver, almost as good as silver, is copper. Next down the list is aluminum, and I mean there's a big difference between aluminum and copper and silver and aluminum. Silver and aluminum are almost the same. Then you jump way down, a lot more resistance than aluminum. Now, I don't know if y'all know what copper is used for besides wire. Copper is used to make brass, to make bronze, to make lots of materials like that. And back in World War II, when we were bombing the mud out of Germany and then later Japan, and way before we even got into the war, we were providing munitions for England and the rest of Europe and other people, and we were using copper like crazy. In fact, they banned the use of copper for civilian purposes. They wanted all the copper to go to the war effort. Well, there's all the wiring for new houses. So people who were building new houses in World War II time, they couldn't use copper. And silver was way too expensive, so they jumped down to aluminum. Now, are there many houses left with aluminum wiring? No. There's two reasons for that. They burnt down. Exactly. Because they overheated so easily because there was more resistance in aluminum than there was in copper, they would burn up. And they did. They literally burnt down. Or people came in and removed all their aluminum wiring and put copper. They retrofitted them or they burned. That's why you don't find houses with aluminum wiring anymore. Just a little thing. So the material is one thing. Okay? Let's go back and get the others. Okay. Let's picture this. Remember, we used water as an example. Let's say we've got a straw that you're going to drink your milkshake through. Big old fat straw like this, right? Okay, it needs a big old fat straw. Because if you tried to drink your milkshake through those little coffee stirrers, that are tiny little things, if you tried to drink a milkshake through that, you're going to pop your ears, okay? Because you're not going to be able to suck it up. It just is. There's one thing. The diameter of the straw, or the diameter. Actually, what it is, it's not diameter so much as cross-sectional area. Of the wire. The bigger the wire, the easier it is for current to flow. The smaller the wire, the harder it is. More resistance in a small wire than in a big wire. Okay? I don't know enough about how they move electricity from pole to pole and stuff like this. My guess, pretty big wire. My guess would be pretty big wire. Another thing, let's go back to our hose type concept. When we were, we have the farm over in Georgia, and several years ago they had a severe ice storm. We had a pretty bad ice storm here. Theirs was far worse, and they had tree limbs down everywhere. And in front of the little 2-bedroom bungalow we built over there are 4 big, old pecan trees. And boy, they broke limbs out of them like crazy. They were big enough trees, they survived okay. But boy, the piles of limbs that were underneath. So we sawed up the bigger limbs and hauled them off to the woods. We took the smaller ones and put them in a pile, and later we're going to burn them. So when we were set up to burn this one pile, it was far enough from the house, I had to run a hose, attached to a hose, finally to get out to the end. Turned on the water full blast at the house, but what came out of the hose pipe, as my grandmother used to call it, a trickle. Because all that length of hose was more and more resistance, so you lost pressure the whole way down. So I couldn't control very well the burn with my hose. So that was the other thing, the cross-sectional area. Oh, we already mentioned the material. And now the length. The longer the wire, the more resistance. The shorter the wire, the less resistance. Okay? Now, there's one other thing, and that's temperature. The higher the temperature, the more resistance, because the things that are in the wire are bouncing around more, so it provides more targets for the charges to hit against, so the resistance goes up at higher temperatures, down at lower temperatures. Okay? So temperature is the fourth thing. Now let's go back and think of our incandescent light bulbs. Y'all have seen them before, especially those clear ones. Have you seen the filaments in those that you see between those poles? Okay. What are some things you note about those filaments? Yeah, they're in a coil, aren't they? Going across, they almost look like a spring. Well, if you think about what's that doing, that's adding length. It only goes between here and here, but that coil, think how long that wire is. Okay, so the longer the length, the more the resistance, the more it heats up, and the brighter your bulb is, right? What's the other thing you know about that filament? Big old thick wire? No! Incredibly thin wire, almost like a hair thickness. I don't have much to show you, but never mind. Okay, that would be, it's a really thin wire. So small cross-sectional area, high resistance. The other thing, that wire used to be made, I think they still are, out of tungsten. Very high resistance, resistivity. Not maybe as much as nichrome, but still very high resistance. So therefore, it's going to get hot faster, hot enough to give off light. Okay. Now temperature. Let's think about that for a moment. The higher the temperature, the higher the resistance. The lower the temperature, the lower the resistance. And remember, if you have a low resistance, that means you can have high current flow with the same voltage. Just about everything is 120 volts, right? So same voltage. So when the resistance is low, the current is high. Okay? Now, what happens? have you ever had a light bulb blow out on you? What usually is the time that it blows out? When you first flip on the switch. Think about this. That resistor in there is cold, right? So therefore, low resistance, high current. If the wire is weak, like it's been used many, many hours, and now the wire is slowly getting thinner and thinner, when you send a large current through there, it blows. Very seldom does it blow when it's hot, always when it's cold. So there's another example of, there's an example of temperature affecting resistance. Okay? That's probably way more than what you really wanted. The material, characteristic of material is called the resistivity. And that would be the same for any material at a given temperature. Silver has the lowest resistivity, copper next, aluminum, gold is shortly after aluminum, and so on. So, here is a formula for resistance based on those features. Resistance, that's measured in ohms, is rho. Now that rho, we see rho in a lot of things, that is your resistivity. Rho is resistivity. Times L, the longer the length, the more the resistance, divided by A, the smaller the cross-sectional area, the higher the resistance. So divided by A, that's your resistivity. The only thing that's not included in that is the temperature. That has a completely different ring to it. So that is those factors, the three of the factors used to determine resistance. Resistivity is from the type of material, the length and area from the size of the wires. All right, so let's go to example 1. Okay, let me clear this out of the way so we'll have room to work. Example 1 here, find the resistance, so we're looking for R, that's resistance, of a copper wire, Cu is copper, okay, 20 meters long, wow, that's one long wire, 20 meters long, with a cross-sectional area of, 6.56 times 10 to the minus 3 square centimeters. That's pretty small. Really, really small. At 20 degrees Celsius. Now the reason that's in there, that's what they measure the resistivity of copper. So the rho for copper is, they give it here, 1.72 times 10 to the minus 6 ohm centimeters. Okay. So, given that, and the formula we just had, resistance, that's what we're looking for. Resistance is equal to rho L over A. Okay? Now, we have a problem here, Houston. This is given in centimeters, this is given in centimeters, but this is given in meters. Most of the time we try to get back to meters. In this case, since the other two are given in centimeters, let's get the meters to centimeters. So let's do our conversion. 20.0 meters, we're going to need to multiply it by something to give us so many centimeters. What unit will go where? Two blanks there. The first is for numbers, second for units. Always put the units in their place. What unit goes where? Something on top, something on bottom. And the choices are meter or centimeter. What goes where? Meter goes at the bottom, centimeters on top. so you can cancel out the meters and get centimeters where you want it, right? Okay. Now, how many centimeters in a meter or how many meters in a centimeter? Now match numbers with your units. What would that be? Say again? How many cents in a dollar? 100. So 100 centimeters, centimeters in 1 meter. That's it. So when you multiply 100 times 20, you get 2,000 centimeters. Okay? They write it as 2.00 times 10 to the third centimeters. Why don't you write 2,000? Okay. Knowing that 2 zeros are significant, the last one is not. So the rho they gave us, 1.72 times 10 to the minus 6 ohm centimeters. Okay, can I erase my scratch work over here? The screen just isn't big enough for the two of us. Okay. No, that's the town. Never mind. Okay. Times the length, which we just determined to be 2,000 centimeters, divided by 6.56 times 10 to the minus 3 centimeters squared. Okay. Now they say at 20 degrees Celsius, we're not really going to adjust for that. We're just going to use it. Okay? Now, if you got your calculators, pull them out. While you're pulling them out, notice here we have centimeters times centimeters. That would be centimeters squared. Here's centimeters squared. So your centimeters do disappear, and you're left strictly with ohms. So 1.72 EE or EXP negative 6 times 2,000 divided by 6.56 EE or EXP negative 3. And what does that give you? Anyone get an answer yet? Zero 0.524 is what they give in the book. 0.524, and the unit is ohms, a great unit for resistance. Okay? Sometimes my ohms look like octopi. I don't know why, but anyway. And that, by the way, finishes 17.5. We're sort of zooming through this chapter 17 because they only have like one example per section. So homework exercises, they got 10 of them. The odd numbers, there are 5. So do any, if not all of those 5 odd homework exercises. All right. Do we have time to start on Ohm's law, you think? 3 minutes? 2 minutes. Well, I just want to remind you what I said before. What Ohm did, he studied voltage, and he found out it was proportional to current. And his constant of proportionality was his resistance. Okay? Therefore, Ohm's law, this is exactly Ohm's law. Voltage is equal to current times resistance. Those are the symbols representing the quantities. The units are volts, same symbol for V, is equal to ohm times amperes. Okay? The symbolic parameters are V is equal to IR, or RI. Usually it's written IR. And the symbols, the units are voltage, volts is equal to current in amperes times ohms, which measures resistance. Okay? That's Ohm's law. Now, what that implies is that, and they sort of do this a little backwards, they put voltage on the horizontal scale and current on the vertical scale. I don't know why they do it, but they do. And then if a material acts like that, we call it ohmic, meaning it has a constant slope, meaning R is fixed, a constant. However, there are certain materials, I'm going to use a different color. What color would you like me to use? Pick one.
Green.
Green, you said? Or red?
Green.
Green. Okay, we'll choose green. If it's non-ohmic, it's not going to be linear. It's going to have curves on it. So we're going to deal only with ohmic materials who have that straight line curve, straight line response, so that the slope is a fixed number, and that's a constant resistance. So we'll be doing, everything else we do is going to assume we have ohmic resistors. Georg Simon Ohm, that's a very French-sounding name to me. It was a physicist born in Bavaria, whose capital is Munich, by the way, just to give you an idea, southwest Germany. And he did a lot of the early work with resistance, basically defined it. Okay, so we'll pick up at that point. Are we out of time now? Pretty close to it. We'll pick up there and talk a little bit more about Ohm's law there. Okay, good deal. Any questions? Got quite a few sections covered, so you have a bit of homework problems you can work on, plus the test that you have. So